Hi, my name is Maisie Anderson, and here's my lab report for Lab 6 for Physics 2212, Magnetic Braking with Faraday. So firstly, what is the purpose of this lab? Well, the purpose is to explore the interaction between the falling magnet and the tube of aluminum foil as the magnet travels through it, thus studying magnetic induction and currents. The experimental model for this lab was the bar magnet falling through the aluminum foil tube, and the computational model was made using GlowScript. The system was the bar magnet and the aluminum tube, and the surroundings was everything else. And as a brief preview of the results, the experimental average time was 0.982 seconds, and the computational time was 2.754 seconds. So, some fundamental concepts for this lab. First is Faraday's law, which involves that changing magnetic field throughout a loop induces a voltage that is proportional to the rate of change of the magnetic flux in the opposite direction to the change in flux, and that equation is shown in the top right. Next is the Biot-Savart law, which states that a steady current produces a magnetic field in the surrounding area, and the strength of the field will depend on the current and the distance from the current carrying section, and that law is shown to the top left. Then Newton's second law, the net external force will be equal to the change in momentum of a system over time, and Newton's third law, which states that every action force has an equal and opposite reaction force. So what was the procedure for this lab? Essentially, we dropped a bar magnet through an aluminum foil tube and measured the time it took for the magnet to fall through the tube. And we did this 4 more times after the first time, so we had a total of 5 runs, and then we calculated the average time from that. And the assumptions that we had to make from this lab were that air resistance was negligible, the bar magnet acts as a magnetic dipole, the only forces are the magnetic and gravitational forces. So for our initial conditions, the length of the tube was 0.46 meters, the width of the tube was 0.01 meters, the inner radius was 0.025 meters, and the total radius was 0.035 meters. The magnet mass as well was 0.025 kilos. And then mu for the magnet was 4.772 am squared. And as we measured through our 5 trials, the average time it took the magnet to fall through was 0.982 seconds. So here's the code that I used for my computational model. These are just the parts that I edited. So first are all of the initial conditions on the top left, and then the definitions of a dipole and the change in flux on the top right. And then essentially calculated all of the different forces acting on the magnet, and then updated the magnet's velocity and position as shown on this slide. And then here are the results. So on the left is the visualization of the magnet falling through the tube, and then on the right is showing the velocity over time. So when the slope is negative and decreasing, that's when the force of gravity was stronger than the force of the magnet, or the magnetic force, which is when the magnet was entering and exiting the tube. However, for the most part, while the magnet was in the tube, the magnetic force and the force of gravity were equal to each other, so the velocity was constant. So to interpret the simulation, which color corresponds to the clockwise current as viewed from above, and which corresponds to the counterclockwise? How can you know? So the red was counterclockwise and the blue was clockwise, and we got this from Lenz's law. What happens to the dynamics of the system when you flip the magnet around? The magnet would still fall, but the current directions would be switched. How does the total time in tube of the real-world system compare to that of the computational system? How might the computational system be made more accurate? The computational model was longer than the real model, which was not expected, and it was likely due to human error in the measurements of the tube. So having more accurate measurements or double-checking those could help improve the accuracy. And then, what does the shape of the velocity versus time plot tell you about the forces acting on the bar magnet? The gravitational force is greater than the magnetic force when the magnet is entering or leaving the tube, but the two forces are equal while the magnet is inside the tube. Potential errors could have been tilting of the tube when dropping the magnet. There could be friction if the magnet bumped the walls, and time measurement inaccuracies or tube measurement inaccuracies. And then discussion, what if the resistivity of the conductor were reduced as close as possible to zero? How would the dynamics of the falling magnet change? Decreasing the resistance would increase the induced current, V equals IR. So a stronger opposing magnetic field would be produced, and the magnet would fall through the tube more slowly. And then, what if holes or slots were cut into the tube? How would this affect the ring currents in the model? The opposing magnetic field would be weaker because there would be fewer current rings in the tube, so the magnet would fall through the tube more quickly. And that's all for this lab. Thank you so much.